So we start. Hope you're getting me. You're getting me?
Yes.
So we'll start with what we were supposed to do today. Actually, part of what's supposed to do today, and that is probability distributions. Last week we dealt with random variables, which I've told you are variables that you can use to model a business process. You create a probability model. So random variables are governed by various probability distributions. This was I want you to note. They are governed by various probability distributions. These are just mathematical models, really, that you can create to analyze the behavior of a random variable. Like if you want to analyze the behavior of a queuing system in a service at a service station, you first of all define the random variable you want to model. Probably it's waiting time or service time, whatever, or arrival times at a service station. So you need to define those random variables first and then represent them by some letters of the alphabet, just for ease of representation. And I told you, you represent random variables by letters of the alphabet or subscripted letters like X1, X2, whatever, because you may have more than 26 random variables. Therefore, you need to find a better way of defining them. So there are broadly two types of random probability distributions. The first one are called discrete probability distributions. These are used to model discrete random variables. Discrete probability, and I want you to go online, even Google Scholar is available, and check the descriptive narrative of discrete probability distributions, what they are, just description of what they are. But generally, they are used to model discrete random variables. These are variables that can take only whole number values. And I talked about that last week, like number of customers arriving in a banking hall. Those are discrete because number of customers can never be fractional. It can only either be please. It can only be a number, a whole number. There are a number of such discrete probability distributions. But here for business students, at this level, we focus on only two. One of them is called the binomial distribution, which is really the essence of today's lecture, binomial distribution. And the other one is Poisson distribution. So you will see Poisson either today or next week distribution. Those are discrete random variables. There are a number, but for business students, MBA, we only look at two. Then you have continuous probability distribution. This will govern random variables that can take all values in the natural number system, fractions and whole number, like stock prices. Stock prices cannot be only a whole number. Stock price can be fractional or can be a whole number. Profit, name them. The waiting time in a banking hall, service time, all of those are continuous with random variables because they're also governed by probability. And to model them mathematically, you use continuous probability distribution. Again, there are a number of these, over 8 of them. For business students, we will only cover one, and that is the continuous probability distributions, which is next week, part one, continuous probability distribution. So today's focus is to start with discrete, and we'll start with the first discrete probability distribution, which is binomial distribution. By means two. Nomial simply means level. Nomial. So two levels. So these are probability distributions that govern random variables that can only produce two outcomes. Two outcomes. Yes or no. Adopt or not adopt, or not adopt. Defective or not defective. Success or failure. These ones can only be modeled using binomial probability distribution. And it has its properties, which I will go through. The properties that a business problem must satisfy to be modeled by as a binomial distribution, that a random variable to be modeled by using binomial probability distributions. So its properties, I've highlighted them in your PowerPoint. There are a few here, and I'll just show them to you in a minute. Now, first, all those experiments that can produce only two outcomes are called binomial experiments. Like if you're doing a survey, a market survey, and you're only asking people to tell you whether they'll purchase an item or not purchase, that survey is a binomial experiment. People will view, some will tell you yes, some will tell you no, some will tell you blah, blah, blah. That's a binomial experiment. Binomial experiments are those experiments that can produce only two outcomes. In football, win or fail, profit or loss, up or down, like fluctuation. So those are binomial experiments. So you can do a binomial experiment, probably say if it's a sales survey, you pick 1,000 people and then you ask them, that's an experiment. They'll be giving you their responses. That now you are doing an experiment that will only produce two outcomes, a yes or a no. When 40 students take an exam, that's a binomial experiment. That's a binomial experiment because they'll be either pass or a fail. A pass or a fail. When you produce items along a production line, you can only have either a defective item or a non-defective. The process of birth is a binomial experiment because you can only have a boy or a girl. It is a coin, binomial experiment. Etc. Those that can only produce two outcomes are called binomial experiments. And they have the following properties of a binomial experiment. Just a minute, I'll check this too. Now, they have the following properties. The first property here, is that the experiment must be repeated a fixed number of times. If it's a birth process, you have got 4 births, 8 births, 10 births, 2 births, a fixed number of times. So the number of trials must be fixed. And these trials are independent of each other. Each trial are independent of each other. It does not mean that when you have a girl in the first birth, you'll get a girl in the second birth. They are independent. They do not influence each other. So that is a critical property of an experiment that satisfies binomial requirements. Number 2 are outcomes. And I've said they can only produce 2 outcomes. 2 outcomes. With one outcome being, and now this is now binomial terminology, one outcome being classified as a success S. Don't change your own. It is success S. Textbooks, you will see success S. And failure F. A success S and a failure F. Failure F. So if you define getting a girl as a success, then of course getting a boy can be a failure, will be a failure. It does not matter which one you call a success, which one you call a failure. It is your definition of what is your opinion is then. As you will get classified as either. You can do either. If you say the defective items is a success, and non-defective is a failure. That is fine. Now, each success has a corresponding probability denoted by probability of S. P of S, it is here. P of S, here. It is here. Which normally in subjects we just call P. And don't change your own. It is P. It is letter P. In the context of binomial distribution, it is P. Right? P. Probability of success is small p. Small p. And the probability of failure, F. Probability of failure, F. F. Probability of failure, P of F. So instead of P here, PS here, you simply put capital F. Probability of failure normally denoted by Q. So probability of P is P. Probability of success is P. Probability of failure is Q. Then the random variable X are the number of successful trials. So you must have the random variable X, which defines the number of successful trials. And we'll give you examples here of experiments that can be considered as being binomial experiments, and those that can be that are not binomial in nature, that are not binomial. So I've summarized these properties for you in a table. So if you want to check whether an experiment is a binomial experiment, just fit this table here. The first column is the symbol. Symbol is n, the number of times a trial is repeated. If you had 4 baths, n is equal to 4. If you toss a coin 100 times, n is 100. If you perform the survey on 1,000 people, n is equal to 1,000. Then P, the probability of success. Then P, the probability of success. And that is in a single trial. So if you define the getting a girl in the bath process as success, then the probability of getting a girl will be P, where the probability of getting a boy will be Q. But since you only have 2 outcomes, P plus Q must be equal to 1. That's when we did under probability, because the sample space here is only 2, S and F. So the P plus Q must be equal to 1. Therefore, Q is equal to 1 minus P. Then X, the random variable that represents the number of successful outcomes. And we did this in under random variables. Then let X be the number of girls, random variables. The way it was, if it was 3 repeated baths, so X started from 0, 1, 2, 3. If there are 4 repeated baths, then X is equal to either 0 boys, 1 girl, 1 boy, 2 boys, 3 boys, 4 boys. We did that under random variables. So you must also define F. If any of these items is not satisfied, then your experiment is not a binomial experiment. And therefore, you can now model it using other probability distribution. There must be 2 outcomes. You must have probability of success. You must have X. So that is critical. So this is the properties I've simply defined in tabular form, in a table form, so that it's easier for you to check, for you to check whether an experiment is a binomial experiment. An experiment is a binomial experiment. Oh, there's nobody waiting out there. So those are the properties of a binomial experiment. So let's take some examples. Let's take an example. That one is too far. One, both that one of cards. There's one here. Let's take this problem and check whether it's a binomial experiment. This is a surgical operation. This is a surgery. In a surgical operation, you can only get two outcomes. Either the surgery is successful or not successful or failure. So a certain surgical procedure has 85% chance of success. Because from where is standard we have just defined, that is P. P is 0.85, the probability of success. A doctor performs 12 such procedure on 12 patients. So you are doing an experiment on 12 patients. The surgical procedure is on 12 patients. So N, of course, is equal to 12. So suppose you define the success as S, let S represent a successful operation and F an unsuccessful operation. So of course, N here is equal to 12. That is our N. P, of course, is 0.85. And since P plus Q must be equal to 1, then you only have Q is equal to 1 minus 0.85, which is 0.15. Now, if you perform the 12 surgical procedures, the number of successes is the same thing we did last week on random variables. The number of boys can either be 0, 1, 2, 3. So the number of success, the doctor can either have 0 successful surgeries, or 1, or 2, or 3, and we can list them, I can tell. We can list them. 4, 5, 6, up to 12. All of them are successful. So this one here tells you this experiment is a binomial experiment and therefore can be modeled using binomial probability distribution. And you're going to do it here. You're going to do it here. And you can cite a number of other examples. So let's take this case here. And this one, I want to take a pen and paper. A jar contains 5 red balls, 9 blue balls, and 6 green balls. You randomly select 3 marbles. So you see, the experiment is performed on 3 marbles. You select them, put them in some jar, then select them one at a time, but without replacement. Meaning, yes?
Bro,
Yep.
there are some people waiting.
Where are they?
Okay.
Can't see them here. We just see. Can't see them here. We just see them. Okay, let me check. So I'm on the second experiment. The other one we have confirmed is binomial. Now this is a jar. You place this jar. The balls are in the jar. So I want you to take a pen and paper. So there are only 5. There are how many balls? 5 red balls, 9 blue balls, and 6 green balls in one jar, mixed together. So let R represent red balls, B represent blue balls, and G represent green balls. So you go to that jar, of course, without checking. You want to pick them randomly. You select 3 balls at random from the jar without replacement, meaning when you select a ball, you check the color, take it back, then shake again. Shake again. Pick another one. Check the color, take it back. There'll still be how many of them? 20. These are 20 balls. But the design of this experiment is that let the random variable represent the number of red balls. That's the most critical thing, the number of red balls. So it means, first of all, this experiment is a binomial experiment to that end. No, the first property is satisfied. N is equal to 3. You have selected 3 balls. And the only 2 outcomes, either a red ball or a non-red ball. If you pick blue and green, those colors are irrelevant. All you need to know is that you're either a red ball or a non-red ball. A red ball or a non-red ball. So what does this one tell you there? Is this a binomial experiment? So I'll show you that this experiment is whether it is a binomial experiment or not, without, no, this was without replacement, so not without replacement. That's the design here. So I want to go to and deal with now, check whether I can show you here whether this experiment is a binomial experiment. And this is how you do it. Are you seeing Excel I've shared? You seeing
Not
Excel?
yet.
Good. So is this an
No,
so
not yet.
Not,
You know, you
not
see
yet,
the
Prof.
problems.
I want to show you that this experiment is not a binomial experiment. And we have noted that a sign that this jar what has got those many balls, and those many balls, you select them this way. You select there were 5 plus 9 plus 6 is 12. You have 12 balls in a jar. In a jar. So what then that this mean? Is it a binomial experiment? That's what I want to show you. Now you're seeing Excel, So now, what I'll do here, we are going to do a T diagram here. So let's do the first selection. Let's do what I'm doing. That's why I want to take a pen and paper. And let's just do what I'm doing here. You draw the outcomes. I want to draw the outcomes here. So the first selection is here. This is a red ball. That's red. And your interest is red and non-red. Red and non-red. That's your interest. Let me just a minute before you do anything. Let me just bring this one here. I'll bring it here. The same tree diagram I do last time. So this is the first selection. So note that right here, red, that we are N. N is NR. NR is non-red. NR, non-red. I hope you're seeing that shape, Now there are 20. So right here, red, and this non-red. So the probability of a red, remember, there were how many red balls? There were how many red balls? There were 5 red balls. So here, P is equal to 5 over 20 because there are 20 balls in that right here, P equal to 5 over 20. Here, along this line here, P is equal to 5 over 20. And the probability of failure, not red, right, Q is equal to 15 over 20. So that's the first selection. Remember, you are doing this, but without replacement. That's the bottom line. Without replacement. So now let's go to the second selection. Remember, you have select a ball, you have not returned it. You remove it. That's what without replacement means. So the second selection, you have 2 options. Either you got a red. You got a red. So you can still get a red and a non-red. Write that one here. Red and non-red, NR. That here, R, NR. Let's deal with that wing first. Suppose you got a red earlier. Remember, you got a red and removed it because it's without replacement. So how many balls are remaining in the jar? How many balls are remaining in the jar?
19.
19.
19.
19.
19. How many red balls are remaining in the jar?
4.
4.
4.
Now we are right here, P is equal to 4 over 19. And of course, Q will be equal to 15 over 19. 4 over 19. And because it's 1 minus P, which is 15 over 19. So this R and NR, non-red. So that's the first part, where you picked a red ball. Now let's go to pick where you didn't pick a red ball. You picked a non-red. A non-red, Non-red. So right here, red, R, this is NR. NR. How many red balls are in the jar?
5.
5. right here, P is equal to 5 over 19. And this one is equal to 14 over 19 because you picked an NR and removed it. So that is, I don't have to go to the third one. Up to here, just shows you this experiment is not a binomial experiment. I'll tell you why. Because P must be a constant. Here, P is changing. P was 5 over 19. Now it is 15 over 19. The next one will be 3 over 18. P must be a constant. So this experiment is not a binomial experiment. A very key experiment in business games. This is what we normally use to design business games for strategy. When you're using probability to define business games, we use balls or jars, among other things, and then define those probabilities appropriately. But critically now, this experiment as it is not a binomial experiment because P is not a constant. It has changed from 5 over 20 to 4 over 19, and it will go up to 3 over 18 somewhere. It's even different down here. 5 over 19 all the way will continue changing. So P and Q must be a constant. So that condition alone tells you that this experiment is not a binomial experiment. So how do I make this experiment a binomial experiment? I'll show you how to make it a binomial experiment. You design your experiment differently. You design the experiment different. How do you define this experiment differently? Where is that probability thing? How you define this experiment here differently? This is what you do. That's how you design it now. Let me just go back to my discrete thing. I will not share the mini first. I want to share with you the PowerPoint. I'll tell you how to change this experiment to be binomial. To be binomial, you just have to change the design. The design, you change the design this way. You come here, this one here. The experiment description remains the same. But now when you are performing the experiment, you select a ball but with replacement. Those are two critical experimental designs. The with replacement design and the without replacement design. So if you design this experiment with replacement design, which means that when you pick up a red ball, you check the color, not the color, take it back. You still have 5 red balls anyway, and 15 non-red. Then if you pick a non-red, check the color, take it back, shake again, take it back, shake again, select again. So each time, the probability to success will be 5 over 20, 5 over 20, 5 over 20. And Q, therefore, will be 15 over 20, 15 over 20, 15 over 20. Am I clear, please?
Yes.
Yes.
So that is making that experiment a binomial experiment. So that is how you check if you have a business problem or a random variable that you want to model using binomial distribution. All you need to do is to check whether it meets those requirements. That's like I've just done here. And then go ahead then and now model it. How do you model it? So let's now go to modeling now. Modeling, creating a binomial probability distribution. That's the model. Construction, right? Construction of binomial probability distribution. That's the first step of modeling. So second step, after confirming that your experiment is a binomial experiment, now the second step now, if it satisfies, then you now construct a binomial probability distribution. Binomial probability distribution, which I'll show you in a minute. But I'll give you there are 3 methods for constructing binomial probability distribution. 3 methods. Method 1, number 1, is called the binomial model. a model, binomial distribution model or formula. Just we call it formula. Binomial distribution formula or model. That's number one. Just a mathematical model, which of course the others will depend on that one. Number two, for in real life, for large problems in practice, you use Excel fx function. Fx. Excel fx, as we were the Excel fx function. Not, let me show you what how fx is written. Because I know what you are writing now. Excel fx function is here. You go to Excel here, I go to Excel. I want to show you what fx function is in Excel. Where's that Excel stuff? It's here. So Excel fx is here. Here, this one. Have you seen where I'm pointing? You see I'm pointing up there? Where the cursor is?
Yes.
That's fx. Are you seeing fx here? This one. All functions on earth are here. Mathematical, economics, finance, name them. They're all here. So you can, by even forgetting the binomial distribution is here. So you also use Excel fx function. So you write fx like this, fx function. That's the second method for constructing a binomial probability distribution. Number two is the binomial table. Nobody these days really bothered about a binomial table anymore in this time and age, because you can create a binomial table on your own using Excel or whichever you go to. They are tables, but every statistics textbook has an appendix. Binomial table is in every statistics textbook. It will not miss. It is there. The problem with those in the table, they might not have some of the properties like P. You may have your own P, but the table doesn't have your P, and you will see it in a minute. Then of course now you are stranded. You use Excel. Excel, you can create your own table using Excel. So these days nobody bothers about a binomial table anymore from a statistics textbook. You either use fx function or you just use the binomial model. And as well, start with the binomial model. I hope you have a pen and paper. I'm recording this thing. I'll send you a YouTube link, so you can look at it if you want. So I'll go to binomial. I hope I'm recording anyway. Yes, that's right. Yeah. So I'll go to binomial. I'll share the binomial. Let's start with the first one, using a binomial model. Binomial models to construct a binomial probability distribution and its measure and its properties you'll deal with. And we're going to do the same thing we did with random variables. So that is it. So write the following. So this is what I want you to write. These ones we need, I can tell you. You don't need this one. You don't need this one in the middle. You can even remove this without a problem. This one. But of course, it is, some textbooks will see it written like this. But just write probability of x is equal to n factorial over n minus x factorial times x factorial. We did these things. N factorial over n minus, this is combination, n combination x. This one here is the right hand side, which is important too, and the far left, times p power x, probability of success, times q power n minus x. We know what n is. We know what q is. So the binomial model is of this form normally, of this form, but some textbooks will just go up to here. They presume you know what this is, NCX. Of course, this n should be up here, NCX, which is just n factorial over n minus x factorial. This is the number of ways of selecting x objects, n objects taking x at a time, where order is not important. We did this last time. So this is n factorial over n minus x factorial times p power x, blah, 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 blah. So this is what you're going to use to create a probability distribution. So what I want you to do to write is this one here. Write this one here. I'm going to use Excel here, but I want you to use your notebook. That's when you will see what I'm doing. We are using the binomial model. This is the binomial model. So I'll copy this model here. I'll copy it, that you see it. Don't want to refer to it from me. You just copy this, and I take it to Excel. Let's get a probability distribution that governs that surgical procedure. The surgical procedure where a doctor performs those many surgeries. We had defined it somewhere. We had defined it, and we had confirmed that is binomial. So I want us to let us determine the probability distribution that governs that surgical procedure. Please just do what I'm doing. There are many ways of doing this, but I'll give you the most efficient way of getting a binomial distribution for the random variable X, the number of successful surgeries. We define that problem elsewhere. Can even still go back there and repeat it. Where were we? We were here. Not repeat, but just to show you let's go back there. What I want to do, what I want to deal with here. We want to describe a probability distribution for this one. Hope that is binomial. This one. Where was it? Was up. So this is the experiment. This is the procedure. This is binomial distribution. Probability distribution. I want to develop. Now, just go back there. Where were we? Here. The surgical procedure was this one. Certain surgical. So you want a probability distribution that governs this surgery. Incidentally, what's the probability that a doctor will get nothing successful? 1, 2, 3, 12, all of them successful. That's what you want to. That is the essence, the objective of this. So here we are just pick this one here because this one we said this one was binomial. So I'll just take these ones here. Take these ones here. And I take them to my Excel. To show you what there are many ways of doing this I can take, but I'll give you only one efficient way of getting that probability distribution. So let me share Excel again. Please, you are going to use your notebook. Me, I'm using Excel because we are not in class. So that I use it as a board. So this is it. So where's that experiment thing? I will just copy it here. This is it. That one. That one. So there is the complete description of that surgical procedure. So now, there are two ways of doing this. You can either use a table to get that probability distribution or just use analytical method. But I'm going to use a table. And a table is more efficient. So the first thing is to have a column here called X. X. Make it larger. I hope you have a pen and paper. X. This is X. X changes from 0 to 12. X here is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's our X's. Get that column quickly, please. List them. I didn't even have to go to 12 anyway. I could have just taken probably 6 surgical operations anyway. But let me just take the experiment as we have it here. Then the next column is N. N factorial. N factorial. So right here, N factorial. N factorial. That's N factorial, small n. Small n. So what is N in this experiment? How many surgical procedures did these guys perform? 12 of them. True? True?
Yes, 12.
So it means 12 factorial is 12 times 11 times, you know what I mean, Remember what you did with factorial,
Yeah.
12 factorial times 11 times, don't do that. Don't do that, please. Times 10, times 9, times 8, times blah, 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 blah. You can multiply. For large problems, you cannot multiply those. Use Excel. For large problems like this, these are large numbers. But when you're calculator, you can do 10 factorial, 12 factorial. But I'll give you, since I'm using Excel here, I'm simply going to give you the result for 12 factorial. How do you get 12 factorial? Here. I don't have to multiply here. 12, there is a function here called fact function, fact. That's for getting the factorials. I hope you're noting those little things somewhere on the side. You are using probably Excel sheet. Not the Excel FX, but the Excel sheet, like I'm using here. So there's a factorial notation here. So I just click FX function here, FX here. Then I come and check that, make sure that they are all functions. Just check here, because me I use it quite a bit. I can change this one here to all. All these functions are arranged in ascending order. All of them are there using the first letter. So every function in Excel is as the first 4 letters of that function. Factorial, the first letter of factorial is fact. If there was another, then you'll go to the second one, factor. If another, then factor. So, but we know here, I know that it's only factorial with FA. So I press F until I get factorial. Fact. Fact. Here's my F. Go up to F, where I get my fact. Fact is somewhere up here. It is here. That is for factorial. Then I simply click OK. So is the factorial of what? It is inside here. Is the factorial of what? Is the factorial of 12. 12. So I'll just simply come here and I put 12 here. That is 12 factorial. This is 12 factorial. And it is a constant whatever value of x. It does not depend on x. It is here. So it is a constant for whatever value of x. So I copy it everywhere here. I'm using Excel. If I'm using the board, I would still do the same. You write it for each value of x. Each of them. Constant for all values of x. So this is the upper, this one here. This one, n factorial. I'm on the right hand side of this equation here. That's what I'm doing here. Then the next one is n minus x. So I create another column here. I hope you're doing what I'm doing here. n minus x column. We know what n is. I know n is 12. I know what x is. X is in the first column because I'm using Excel. I just pick this value, corresponding value of x. So 12 minus 0 is 12. 12 minus 1, of course, going down up to 12 minus 12. So that's the column for n minus x. I'm still on the right-hand side of the binomial equation. Then the next therefore is n minus x factorial. So it is this thing here, factorial. Here. N minus x factorial. Which again is just, come on, n minus x factorial. Which of course we know is again fact. Since we know it, I put an equal sign, it is fact here. Fact of what? Fact of n minus x. That's where I am now. Okay. Fact of n minus x in the bracket here. So that's the first one. 12 factorial is just that. Then I go to 11 factorial all the way to 0 factorial. That is n minus x factorial. I'm repeating. I hope you're doing what I'm. So I'm done with this one. I'm done with this one. Now go to x factorial. X factorial is here. I'll just put it again. It doesn't matter where it is. Where is x? X is the first column in Excel here. It is this one. That is fact. The first value of x. First value of x is 0. So I'm using Excel. When you use a calculator, you'll get the same. 0 factorial, of course, is 1. 1 factorial is 1. And you'll see it will just be the inverse of this. You just see. So this is it. So that is my x factorial. That's my x factorial. So we are done with these ones. We are done with this. We are done with that. So now we go to here. Here. P power x. Please write here P, the way it is here. P raised to power x. Means since I don't have that one, I just write the normal way using Excel. P raised to the power of x. You write it this way. We know what P is. P here is 0.85. It's here. 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 So it is the first one is the first value of x. So of course, it is basically 0.85 raised to the power of where I am here, of this x here. That's the first period, 0.85 power 0. The next one will be 0.85 power 1, which is just 0.85. Then I do it for all values of x. All values of x. Let's do to 3 decimal places. I'm done with this one. I'm done with p power x. Yeah. Now I'm on q power n minus x. Again, you write the normal way, the way it is written here. Q power n minus x. Q power n minus x. I'll write it this way myself. Q raised to the power of n minus x. We know what Q is. We know what Q is. Q is 1 minus 0.85. So it is 0.1815. So it's again, now it is 0.15 raised to the power of n minus x. Where is my column of n minus x? It is here. On my column. Again, I'll do it to 3 decimal places. I'll reorganize. Then I do it to all values of x. Let's do it to 3 decimal places. To 3 decimal places. We just change it to number form so that it is clear. Number form. So second, so that you notice, you don't see those things, the scientific form. So I've converted my left-hand side of my binomial model into a table. And it is here. It is here. So that's it. What I'm doing all this so that I get the probability of x. That's what I'm doing. P of x, this one. For each value of x. So the last column here is P of x. Probability of x. Probability of x. Please listen to what I'm doing here. Probability of x. I'll go back here. What are the probability of x here based on the right-hand side? It is probability of x, you check on the right-hand side of this equation here. And this equation tells you that you go to the right-hand side, the first thing you do is what is in the numerator here on the right-hand side. What's in the numerator? What's in the numerator are the following. N factorial times this times that. That's in the numerator. Even if you're using your calculator, you need to know what's in the numerator. Because even your calculator has got these provisions of brackets. So you deal with you multiply the numerator items, which is n factorial times p power x times that, divided by this times that. This is in the denominator. The numerator are these 3 items here. The denominator is this for each value of x. So what am I saying here in short? I'm going to multiply n when x is equal to 0. That's where I am. I'm going to multiply n factorial column. Where's n factorial column? I just do, because I'm using Excel, I put a bracket here. Where's the x factorial column? N factorial column is this one. N factorial column is this one. Times p power x. times p power x column. Where's p power x column? Times this one. Times p power n minus x. Times p power n minus x. Where is that? This one. Then I put bracket, because I'm using Excel. Then bracket. Bracket what? N factorial divided by what? N minus x factorial. Where is that? This one here. Even if you put in your calculator, that's what you do. X factorial. Where is x factorial? X factorial corresponding is this one. Then I put a bracket. Bracket. So that's the probability that you get 0 successful surgeries. 0 successful surgeries. And it is 0, I can tell you for a fact. There's here. Even if I do it for 2 to 3 decimal places, it is here. 0. Then I do it for each value of x. Each. So for that to get 1 successful, 2 successful, 3 successful, 4 successful, all the way that all are successful. Those are the probability of getting each of those successful surgeries. This is the easiest way to construct a probability distribution table for the random variable x. Please copy this table. Just give you a few minutes to copy that table fully. But before you copy the table, I want to copy everything here. What's important in this table here? So therefore, let me write it for you. Therefore, so that you will see you put it on your notebook. Therefore, the probability distribution that governs the random variable x, the number of successful surgeries, is given by. What's important in this table are these columns. This column and the last column. The others are methodological, I can tell you. This one. So the table here, so this is the probability distribution that governs this random variable x. This table here, this one, the last one. That's the table we want. This is the binomial probability distribution of the random variable x. The binomial probability distribution of the random variable x. I'll do it number form. That will remove scientific notation. It's the same thing anyway, but I just want to deal with it here. To 3 decimal places, say. To 3 decimal places, and we are done. So that's your table. That is the most important. That's the table. This is the probability distribution of the random variable x. Here's one here. Everything else in between are methodological. From all these things are methodological, these ones. Methodology to enable you get this. So this is the table I would want you to know. And this
Excuse
table
me,
is a
Prof.
very important table.
Excuse Prof.
Yes, please.
Could you please click inside x factorial so that I could see the formula that you used to get x factorial in
Fact,
column E?
fact. It is
Column
fact.
E.
Fact.
No. Column E, the next column.
Hey, it's the same. This one is fact. Fact of
Okay.
A3 now, eh? Here,
Okay.
Because the first value of x here is there, eh? But you know, this thing is in here. You don't even have to think about it. It's here, eh? All you need to remember that factorial is gotten from the fx, eh? And the function is fact factorial, this one, eh? They're all here. You, by the end of this topic, you know how to use this fx function, eh? That should not even worry you, eh? You know how to use this one here, going forward, eh? So this is important. So now I'm just going to change something here. I want you to, later on I'll show you why. I'll tell you why I'm doing this. I want to write my P here. P here was 0.85. 85, eh? 0.85. And what was my Q? My Q was what? That 1 minus that, eh? 1 minus 0.85. I want to build it inside here. You'll see why I'm doing that in a minute. I'll tell you what I'm doing. So this is why 0.85. So what is not changing here is 1 is not, B1 is not changing. So 1 is fine. Come here. Just also just pick, instead of 15 here, I pick this one here. Therefore, this also is not changing. Not changing. And I just do it for all. I've not done anything. I'm just trying to build the formula there. That up there. I've just put my 0.85 here as a formula and 0.15 here as a formula. Cell references are here. So you see how I'll do what I'm going to do that. So please copy this table fully. And please, if you have a question, ask now. So this is the probability distribution of the random variable X. So note. Just note. Are you done with copying? Give you time kidogo.
Give us time.
So.
Excuse me, Prof. Please
Yes.
click on the first
There?
where you have the column B, the formula.
Formula for column what? Which column?
Column B.
Column E.
B.
D. This one, eh?
Yes. B.
This one.
Just go to your left.
B for boy.
B
Oh,
for
B for
boy.
boy. This one. You just
That's
fact.
D. Now go to the next.
You
Yeah,
just
that
fact.
one.
Fact
Okay,
is the
fact.
factorial of 12 is N, eh? N is 12, eh?
Yes. Okay.
N is 12, eh? There were N surgical operations, eh?
Okay.
Clear? If there are 6 operations, you just put 6 here. If there are 20 operations, you put 20. You know?
Prof, are you able, Prof?
Yes.
Are you also able to click on H3, intersection H3?
Edge.
Is on to see probability.
Give me the heading
H3.
of the column. Give me the heading of the column.
PX, probability
This one.
X.
This
H,
one, what I've
H.
done, you know, this
Move
was
to PH, the next one, probability PH.
this one.
PX, the next one.
PX now is
That one.
PX,
Yeah.
you have to come here. PX, you have to come here. Eh?
Yeah.
This is how you build this thing, even in your calculator. Eh? You need to know what's in the numerator and what's in the denominator. Eh?
Sure.
Eh? These are mathematical things now. Eh? So the numerator is n factorial times p power x times this column. This one is the n minus factorial column times p power x column times this column. Divided by n minus x factorial times x factorial. That is the right-hand side of that formula, and that is the p of x.
Thank you.
That I'm doing this so that you see, see how you use your calculator. With your calculator as these functions. Eh? Any other question? Good. So this is important. Now let me give you 2 minutes. Eh?
Please click on n minus x, where you have 12 fact, the formula used. Prof.
You've said the right-hand side of the formula is P of X. Prof.
I think now you're okay. So now this is important. So now from this table, the yellow one, you can now do the following. These are now some of the outputs you can get from this table. You can get the first thing is that you can construct determine specific probabilities. And I want us to write those probabilities down as an example. Number one, the probability of this doctor or this surgeon getting at least 3 successful surgeries. Just write in words, that the doctor will get at least 3. Number one. Number two, that the doctor will get 7 successful surgeries. I'm just picking examples, right? That's number 2. Number 3, that the surgeon will get between 6 and 11 successful surgeries, inclusive. I add that word, inclusive. That's number 3, I want to cover you everywhere here. Number 4, that the doctor will get between, say, 4 and 8 successful surgeries, exclusive. I'll tell you what does those things mean in a minute. Exclusive. So those are individual probabilities. I want to do them one by one. Then you can derive your own. So that when you go to this doctor, you know, this one can enable a patient to decide whether to visit this doctor or not. I can tell you. If the probability of getting a surgery is too low, you have no business going to that surgeon. You only go to a surgeon where the probability of success is high. Because surgical operation is probabilistic. It is governed by uncertainty. So hospitals can also use this to make a decision on the doctor's performance, you know, the likelihood of his surgical procedures being successful, because they have historical data, which we can now use to determine the probability distribution that governs his or her surgical operation for a given problem. So it can be patient-based decision or hospital-based decision. And you can generalize to any other entity, even in the business world. You can. I can tell you can. Even then dealing with the queuing in the bank, you can. Likelihood of getting a long queue or a short queue, whatever it is. So let's deal with these cases. Let's go to the first case. Number one was getting what? At least what? At least 3, eh?
Yes.
At least 3, eh? Let's start with that one. At least 3, you convert all those questions in mathematical form. At least 3, meaning this. And please write these things down. And I hope you know how to write greater than or equal to, eh? You know how to write greater than or equal to? So just write here. The first question here is that P is greater than or equal that X greater than or equal. So write greater than equal to sign here, greater than or equal to. Greater than or equal to is written like this. Because I can't fit here. That's less than it. This one here is strictly, sorry, what's greater than here? This man's. That's greater than. This is strictly greater than. So if X is greater than 3, that will get more than 3. Meaning 3 is not included. But greater than or equal to, you need to put in here. You need to put a dash down here below this line, before this greater than here. You know how to write that anyway. But I'm going to write it in Excel form. So this is just like that. Greater than or equal to 3. Is equal sign. Things on that side. Don't write it this way. Write it the normal way. Because I can't waste your time designing it here. That is greater than or equal to 3. Greater than or equal to 3 means you add all those probabilities. So the probability that X equal to 3, plus the probability that X equal to 4, plus the probability that X equal to 5, plus the probability X equal to 6, X equal to 7, plus the probability X equal to 8, plus etc. You add all of them. Add all of them from 3 and above. You will get the probability you want, I can tell you. So meaning that I only need to add these things here, these ones. I need to add this, all of them. Then I'll get the probability that a doctor will get at least 3 surgical procedures. But I can tell you this one. You must be innovative when you do these things. This one here, we know for a fact, and I forgot to do this. When I sum these probabilities, I should get what anyway? I should get what? We talked about this last week. I should get what?
1.
1.
You need to write here sigma P of X. Sigma notation is here. Up here, sigma P of X. P of X is here. Is equal to 1. When I sum all these things, I will get 1. Not can, I will get 1. This one, there must be 1. This assists you to even simplify this problem. So instead of adding all these things here, all of these things, the best way is just to add these 3, subtract from 1, I get the rest. So this would, alternative would have said, I would just say 1 minus 0 plus 0 plus 0, which is equal to 1. So the probability of getting at least 3 is equal to 1, I can tell you. The rest are just 0. Is equal to 1. Am I clear, please?
No.
Yes.
So what was the next one? What's the next one? Number 2 was what?
Successful surgeries.
Eh?
7 surgeries.
7 surgeries, eh?
Yeah.
7.
Yes.
It is here. 0.19. 0.019. The doctor will get 7 successful surgery 7. Is that what? 0.019. Number 3. And you need not to write that in mathematical form. It is P is equal to X, probability of X is equal to 7. You need to write it down here. Because we're doing statistics, eh? You need to write it here. So this one here, it would just be this one here is equal to 7. 7. Next. Next, what?
Inclusive.
Huh?
Getting between 6 to 12 successful surgeries inclusive.
Between 6 and
12.
or 6 and 12 inclusive, isn't it?
Yes.
Meaning that this is now what you do. Again, you write this in mathematical form. Then you just write the stories. Eh? So you come here, then you come here, then you say, between 6 and 9 inclusive. Eh? So you come here. Let me write it for you here. So now it means it is between 4. X is between 4. It's less than or equal to. So you need to write less than or equal to here. The normal way of writing less than, we put a dash below this lower part of this. And I'll put in Excel form. Eh? That one there. That is less than or equal to less than or equal to what? X is between 4 and 12, eh? Then this one here.
It's 6 and 12.
6 and 12, eh? So I come here, this is 6. Then 12 is here. Is less than 6 is less than or equal to X, less than or equal to 12. Less than or equal to 12. Meaning that 6 and 12 are included. So you'll have probability that X equal to 6 plus a probability equal to 7 plus a probability equal to 7, all the way up probability X equal to 12. So it means you'll add all these things here. These what? All of them. This what? Because the X, 6 and 12 are included. Last one. Last one. Between what and what exclusive?
4 to 8.
4 to 8 exclusive. You must check those the way those relationships are, right? Exclusive, because it cannot be inclusive to the left, but exclusive to the right. Eh? You need to check the way they are written. Eh? So this is okay. So 4, this is 4. 4 and 8 exclusive, meaning that 4 is strictly less than X and it's strictly less than 8. So they're exclusive, meaning that 8 and 4 are not included. So you'll add the probability that X equal to 5 plus the probability that X equal to 6 plus the probability that is equal to 7. You are done. So that is now you can say, so if I went to this doctor, what's the probability that between 4 and 8 of his surgeries was successful? You want to make a decision. Or whatever you want to decision you want to make and move on with your life. So this is important as a derivative, these probabilities. So now that, next, note also number 2, that from the probability distribution table, one can derive what is called cumulative probability distribution tables. Cumulative probability distribution tables. Cumulative. To cumulate is to add successfully. Cumulative. What is cumulative? Probability distribution tables. Cumulative probability distribution table. To answer 2 questions. To answer either of the following 2 questions. That's what this cumulative probability distribution will answer. The following 2 questions, either of the 2. The at most question and the at least question. I'll tell you what those means. The at most question and the at least question. The at most and the at least question. So let's start with the at most question. This relates to a probability distribution that let's use this surgical procedure. That this is related to the probability of getting at most a given value of X. At most a given value of X. That's the at most question. So what's the probability that this doctor will get at most 0, at most 1, at most 2, at most 3, at most 4, at most 5, etc., etc. That's the at most question. So let's generate the at most, the cumulative probability distribution that answers that question. Please, then create a column here. Let's have X here, X column here. Because we want at most a given value of X. At most a given value of X. Then I need to get my cumulative probability. Cumulative probability at most less than L. That's the at most, right? The cumulative probability less than. Less than means at most, eh? Less than is at most, eh? Less than is at most, eh? Less than or
Yes.
equal to is at most normally, yeah? So just call it less than. I'll call it L. Less than. Community probability less than. So what I'll come here and I answer the following. This is how you derive it. You come here. What's the probability of getting at most 0? The probability of getting at most 0 is just this. It's the same. At most 0 is just this. There's no other x value below 0. Now look at the way I'm getting now at most 1. At most 1 means getting 0 and 1. Because 0 is before 1. So all I need to do is to add 0, this to that. Add 0, this one here, to the probability of 1. Because 1 and at most 1 includes 0. So I'll simply add these two. I add this one here. Plus this one here. That is at most 1. At most 2. At most 2, we will add all these things. This plus that plus that. Already up to here, I have added these two, eh? So I simply add the at most 1 to the probability that x equal to 2. That x equal to 2. By the time I reach ahead there, we'll be okay. At most 3. At most 3 is adding all these things. Already I have up to here is at most 2. So I just add this to that, eh? Add this to that. Plus the probability that x equal to 3. That x equal to 3. What will be this one? Here. Somebody? What will be there? At most 12.
1.
Eh?
1.
1. Beautiful. 1. So all I need to do
1.
is copy this thing. I can copy this. And I bring it everywhere here. Because I'm using Excel, I don't have to waste time there. So this is 1. That's at most 1. At most 12 is this. At most 10 is this. At a very important table in making decisions. A very important table. The cumulative probability distribution less than. A very important table. Now let's go to the at least question. The at least question that the doctor will get at least a given number of successful surgeries. At least a given number of successful surgeries. At least 0, at least 1, at least 2, at least 3, at least 4, up to at least 12. So again, I come here and I get that table. I get that table of at least. I simply pick this. At least means greater than anyway. But greater than or equal to. And now I need cumulative probability greater than this one here. CPG. What call it? Yes, CP greater than. That's at least greater than or equal to. So again, I pick my values of it. Those are the ones I want there. Then I have them here. So what's getting at least 0, at least 1, at least 2? The best way, normally in statistics, for greater than, you start from below. You start from below. Going upward. Of course, you can start from up, but for ease of appreciating, start from below. So I come with a probability of getting at least 12 successful surgeries. There's no more than 12 surgeries here. So at least 12 is just the probability of 12. It is here. At least 12. Because there's nothing beyond 12. Then at least 11, I add the 12 to 11 one. I add this. Plus the 11 one. At least 10, I add 10. I would add 10 to 11 of the one of 12. So I'll just add at least 12, at least 11 to the probability of 10. Probability of 10 is here. What will be up here? Here. What will be there?
1.
1. Beautiful. 1. So all I need to do is to copy this. And I bring it here. And I'm home and dry. Now there's a problem somewhere there. I added something wrong somewhere here. So this is at least 12. So that's okay. I know what I did here, which is faulty. As I meant, just give me a second. Where is this one here? That's that one there. Something faulty somewhere there. It is this thing here. Blah. That one there. Eh? No, I know what I've done. Sorry about this. I'm using the wrong thing. I'm using the wrong thing. Don't worry. Don't worry about this. So I need to pick this one here. I'm adding wrong things. And I'm on this column here. That's where I am. That's where I am, Spencer. So I do all this. And I get 1. That's what we have said. A very important table. Very important. Very important table. So I want you to copy those 2 columns. Copy those 2 columns. The cumulative probability distribution less than, and the cumulative probability distribution greater than. All these things we are doing now, we did them last week on random variables. The only thing we didn't look at what they're at least cumulative, but they are there. But it's the same thing anyway. So copy those 2 columns, please. Copy those 2 columns. Very important columns. Don't ask. If you are not getting anything, please ask. Ask. Now, any question, please? Next is to go to, I'm repeating what we did with random variables. In fact, that's part of the reason why we did that. Because we use the same procedure here to analyze binomial processes, binomial experiments. So I've gotten the probability distribution like I got for getting a boy or getting a girl. Remember. And now I've gotten the cumulative probability, which of course we didn't do, but of course that was another side. Then I've also got an individual probability of getting one boy, two boys. Now I'm dealing with successful surgeries here. Next is to draw the probability histogram. Every random variable X has a corresponding histogram to show you the shape of that distribution. The shape in statistics is a visualization technique. Again, very key. Once all these days of analytics, big data, visualization is very key. You need to visualize the shape of a distribution because that shape has got implications, really, in the deeper analysis. Like when you go to inferential statistics, the shape of a distribution is critical. And here we can only draw a histogram or a bar diagram. And we drew a probability histogram last time. You draw a histogram using this probability distribution here. You can even draw it for this which is called cumulative probability histogram. You can, but I'll do it for this. All you need is to plot this on the x-axis and this on the y-axis. And because I'm not having any here, I'll just draw two columns. You'll sketch. Two axes, x and y-axis. So the horizontal axis labeled it x, the vertical axis labeled it p of x. Then you create your own scale. Just don't do it now. I'll give you the scale to create here using Excel. So I'll come and just plot this. I'm just sketching. I'm sketching. Sketching here, I'll just insert a histogram here. A probability histogram. In Excel, they are there. So the histogram is here. So that is the histogram of this distribution. Correct? Then pick the two columns. Me and do this. Need to get this clearly. This one here. This is what I want. This data. So I draw a probability because I'm sketching. That's the histogram. This is what you'd get if you were to draw it. Of course, this is not one. What is this? Horizontal axis is 12. Is x. What should be here? Because I've just sketched. What should be here? What is this value of x? This one. Anybody? I want you to appreciate this thing. Anybody who can see? What's the value of x? The first value of x here is what here? Here.
0.
0. So this is 0, and this one should be what anyway?
12.
12. So just 0, 1, 2, 3, 4, 5, 6, up to 12. Because I've just sketched. So you need to have here 0, 1, 2, 3, 4 bars. You draw a bar over 0, a bar over 1, a bar over 2, like this bars here. Because the first one is 0, that's why it is just on result here. The next one is also 0, that's why you can't see it. The other one is also 0, 3 is 0, 4 is 0, 5 is 0.01. You can start to see the bar kidogo, then 6, then 5, then 6, of course, 6, of course, 0.04, 7, now you can see it, 0.019, this is 8, this is 9, 9, of course, this is the bar. This one here is what? Is 9, this is 10, this is 11, and that is 12. The vertical axis here is P of x. The horizontal axis here is x. I've created a scale here for you, 0.00, 0.05, 0.1, 0.15, 0. That's the scale. You can draw it yourself. The key thing here is the shape of this curve. It is negatively skewed. The longer tail is to the left. The longer tail of this distribution is to the left, meaning that as the number of surgeries increases, the probability of success increases. As the number of surgeries increases, the probability, then as the number of successful surgeries increases, the probability of success is increasing. That's what it's telling you. And it's consistent with the value of P. The value of P was 0.85. It was very high, very high. A very important histogram for making decisions.
Prof, would you kindly repeat on the explanation of the histogram?
You see,
Kindly.
the longer tail, the tail of this one here is to the left. Are you seeing this? Are you seeing the longer tail is to the left? The longer tail going from zero, then it starts rising a bit like that. Are you seeing this? The shape,
Yes.
That's called negatively skewed, Meaning that as the number of successful surgeries increase, the probability of success is increasing. The probability of success is increasing. It means that this doctor, if successful surgeries, the likelihood of getting successful surgeries are higher with a higher volume of surgical procedures. That's what he's saying here. There's nothing much. That's what he's saying here. This is negatively skewed. Negatively skewed. And if you were doing a student passing or failing, and you get negatively skewed, it's the same interpretation. The same interpretation.
Wait, so Prof, you're saying the more experience he gets, the more surgeries?
No. The more surgeries he performs.
Yes.
The more surgeries he performs, the more successful surgery, the higher the likelihood that he will get a successful surgery, Because probability is a likelihood,
Okay.
Clear?
Yeah, thank you.
Now I'm going to simulate for you. I'm going to simulate for you and show you what happens. Suppose, and that's why I changed this. Yes, please.
Does it mean, considering this data with the whatever we are getting, does it mean this, if you are going to this doctor, it is a problem? Because he has to, for you to get to be successfully done a surgeon, he has to do so many of them.
No. The data you have, the data you have. Let me tell you where this is coming from. Let me tell you where it's coming from. What was the probability of P? What's the probability of P? What was it? P was what? P was 0.85, is it?
Yes.
So this doctor has a higher likelihood of getting successful surgeries. Just by P alone, P alone,
Okay.
To 0.85,
Okay.
So it means that as the number of successful surgeries X increases, the likelihood, the probability of getting a successful surgery also increases,
Yes.
They also increase. They are directly related, The number of successful surgeries and the likelihood of getting a successful surgery. They increase directly. They are not inverse, The converse, let me simulate you. Probably that will make it better for you, Better for you in terms of understanding what I'm saying. Suppose I just came here because I'm simulating, and I change that successful surgery result to 0.85. I change it to 0.7. 0.7, Meaning Q is what?
0.3.
0.3. Good. That's why I wrote here as a formula so that you can see I can simulate for you. Suppose I change this one to 0.7. 0.7. Q is 0.3. You see what's happening here? You see what's happening here? The shape of this curve changes, Let's change to 0.6. 0.6. I want to go to the extreme, 0.6. Look at what happens. Let's go to 0.5. The probability of success is equal to the probability of failure. Perfectly symmetric. In real life, in practice, this is what you would want of this doctor. This one here. This shape is what every surgical procedure should take. This distribution is which is perfectly bell-shaped. You know, the technically it is called the normal distribution. In fact, this is the normal distribution. That under normal conditions, the distribution of successful surgeries ought to take this shape. It should never take extreme shapes. Never extreme shapes, because nobody, of course you can't achieve this, but we normally we want to force a surgical procedure to go this path, to take this path here. Well, this is the distribution under normal conditions, which is theoretic, a theoretic position. This is the more likely case of a surgical operation in this case could be of any other binomial experiment. So I change this now from, I'll let P now be 0.4. Now I'm decreasing C. Let me go to 0.2. Can I go to 0.15 instead? I've now changed them. The probability of success is now very low, 0.15. The probability of failure is very high, 0.85. Now you can see that as the number of surgical procedures decreases, the probability of success also decreases. That is confirmed by the value of Q, which is 0.85. The probability of failure. The probability of failure. Now, this is the value of visualization. Visualization. You want to get the optimal probability of success for a given surgical operation. Because you have a number of surgical operations there. You get the optimal, the best value of P for that operation across all doctors. Then get the average. Then you can say that this hospital, this is the average, the likelihood, the average probability of success for this surgical procedure based on past data. But theoretically, if the desire is to have P to be equal to Q, which is 0.5 plus 0.5 is equal to 1, of course, which you cannot achieve. You cannot achieve. So this is a very important tip, a very important distribution, visualization, using a histogram. And I told you last time that where we are now, because of analytics, it's not 90 students who should deal with this thing. No, every analyst should be able to know how to use visualization technique in analysis. So that is the histogram. Lastly, we did the histogram last time. We would have done it even for boy girl last time as in class. Now let's go to the last one, summary statistics. Summary statistics. The average number of successful surgeries. Critical. What's the average number this doctor can ever, and the accompanying standard deviation. Let's go to summary statistics now. Summary statistics. And that's the last thing we'll do today, because we are doing online. I don't want to belabor you. So let's go to summary statistics. We dealt with, I've just copied the same data. I'll bring it here. The same result, I'll bring it here, so I don't interfere with those things. So this is my summary statistics. Just copy the same distribution. You don't have to copy it. If you have a place where you can get the mean, I'm even going to show you the easiest way to get the mean anyway. I don't want you to bother with many things there. But I'll give you the two methods of getting the mean and the standard deviation. What is the average number of successful surgeries? Last time what we did was to multiply X times P of X. We did X times P of X, then we summed them. We got the mean. What is this now?
Control shift.
Control shift, eh? Control shift, eh? Eh? Where are they? Hey. Where's home here?
With the upward arrow. Control shift with the upward arrow.
I know what I did. I know what I did. But now we are too far. The upper arrow, what have I done? Anyway, let me see.
Control home.
Yeah. I know what I did. Now we are there. So to get P, let me just put this to 3 decimal places, like we did it earlier, so that we don't have to belabor with many decimal places. With 3 decimal places, yeah? We do the same thing we did last time, incidentally, by simply multiplying x times P of x. We did that. So come here and multiply x times P of x times probability of x. That's what we did. Then I multiply this, multiply x times the corresponding P of x. This is a longer method. Don't ever use this method. I'll show you what to do. That is the first one. I do it for all values of x. We multiplied last time like that, incidentally.
Prof, your values are inverted.
Eh?
Your values for px are inverted.
Ah, this one here, eh? Oh, so I need to go back there. This one here. Why were they inverted? Why? Ah,
because you changed to p. P is...
I mean, you know what I did here? You know, don't worry. Yeah, so that you have the same thing. Let me just change to 0.85, eh? I think that's what I want, eh? You want 0.85, isn't it? Now you're okay. Now what I have here is the same thing you have, eh? Good. They are here. I'll copy them again. Because you need to have the same values, actually. That is consistent with what you have. Just come here. Okay, this is where I am. Copy and special. Now we're okay. So you just copy them and do what? And multiply them, eh? Multiply them. That's x times P of x. That times that. Just a minute. Just a minute. There's a problem somewhere. There's a problem somewhere, I can tell you for a fact. And to see what I've done here. Now we are okay now. Then you multiply x times P of x. Good. Then sum of them. Sum of them. X sigma. You sum these things, eh? We did this last time, eh? We sum them. That's not true. Yeah, that could be just true, incidentally. 10.2. 10.2 is the average number of successful surgeries is 10.2. 10. 10. So this sigma x times P of x. Sigma x times P of x is equal to this. 10 successful surgeries. That's mu of x. Mu. You'll see it in a minute. That's the mean, eh? The mean number of successful surgeries by this surgeon anyway. They on average, you will get 10 successful surgeries, which is consistent with that shape. Out of 12, he's getting 10. Very high. Very high. Now, alternative method, the easiest. For binomial, the mean. You don't have to do what I've done there. The mean is basically n times p. For binomial, mean, I'll just write in words here, is n times p. N times p. That is the number of times that experiment was done times the probability of success. This experiment was done 12 times. The probability of success was 0.85. So when you apply n times p, you get 10 successful surgeries. So for binomial, don't go this path. Just multiply n times p. You get your probability the average number of successful surgeries in this case. So that is N. That is the mean, the average number of successful surgeries. The average number of successful surgeries. N times P. So don't go this long path. Next, standard deviation. Standard deviation, we said last time, also, you subtract X minus 10.2 in this case. Then square them. You subtract those two and square them. We did this last time. Let's do that one first, because I know what you're going to do, so that we don't complicate it. So it is basically this one here. Correct? Which is the first value of X, of course, is 0. Is 0. 0 minus 10.2 squared. That is the deviation. That's the squared deviation. The squared deviation. We did this again last time. Then we multiply this by the corresponding probability of X. We did this under the with random variable. You would multiply this by the probability of X times the corresponding probability. Then sum. So we did what? You don't go through this part, but I'm still giving you that. I'll give you the alternative. This one here. So that is that one there, which I can do to normal numbering system. Normal numbering system there. Then I do it for all. So that is, those are the squared deviations. Then I sum them. Again, we did the sigma of that column. Sigma of this column here. 1.53. That is the variance. The variance. Then we get the standard deviation, the square root of the variance. The standard deviation is the square root of the variance of X. So what's the square deviation? The standard deviation here is the square root of this variance here, raised to the power of 0.5, square root. So the square root there is 1.2. So you can get 10 successful surgeries plus or minus 1. Because you cannot get 1.2 successful. It's 10 plus or minus 1. So between 10 and 11. This is the standard deviation. You get the variance? And again, for here, you don't use this path. The variance for binomial, variance for binomial is basically NPQ. N times P times Q is the variance, which you can show that mathematically, which is just 12 times 0.85 times 0.15. That was the variance. That's the variance. 1.53. It is here and this one here. Therefore, standard deviation is basically 1.235. The square root of this. So again, so this is a longer method. This one. The method you use is just this. Mean is NPQ. NP. Variance is NPQ. So S is the square root of NPQ. The square root of NPQ. So those are the critical summary statistics for binomial distribution. The arithmetic mean and the standard deviation. And the standard deviation. So we are done with the binomial. Now I need to show you the other method of getting this. That one is easy. Here, the other method of getting this. I told you there are two methods of getting this. The binomial model, the Excel fx function, and the binomial table. So Excel fx function, I'll just show you here. And please just take note. I want to show you how to get Excel fx function here using this, using to get that column there. Now to get this column, we use Excel fx function, this one here, the probability distribution, this one. So this now just write the same thing here from fx. All I need to get from Excel is just this one here. That's all I need from Excel, nothing else. Probability of x. Probability of x is what I want from Excel fx function because values of x's are mine, I know them. All I need to get is this. How do you get this? Please check, look at what I'm doing. Binomial distribution starts with the first four letters is by B-I-N-O. So if I were to go to fx, I would look for a function called bino. But I will not get it because there are other functions that with the first four letters bino. So you go to the next one, binom D, or blah blah. I'll show you the function that you can use to get this distribution here. X with a corresponding P of X. X with a corresponding P of X. So I come to fx. Here, please check what I'm doing. Then I make sure that if you don't know, if you know, then you'll just come here and pick statistical functions only. But just do all up here where it's appearing all there. Then I want a function starting with B, binom distribution. So I come here and I look for D. Yeah. I click anywhere inside here in any of this. Then I press B until I get binom.dist. Why is this thing not going down? This is for large problems. Binom. So I'm pressing B until I get, when you see binom.dist, you tell him. We are almost there. B-I. I know what it is, but I'm going to tell you where you get it from. Binom.dist. They are there. So you can either use this one here, binom.dist, this one here, or just binom.dist. But you normally use binom.dist. It is here. That's binomial distribution. So if you want to type it in, you will put an equal sign, then just type this one here, binom.dist. So I come here and then I click OK. Are you seeing that, please? You see that?
Yeah. Yes.
Then I click OK here. I get a dialog box. Read the dialog box. Dialog box is there. So I need to fill this dialog box here. So I click here. When I click here, read below here where I'm pointing. It tells you what should be there. Numbers. The number of successful trials. The first number of successful trials is where the cursor is. The cursor is where you have x is equal to 0. So I just pick the where x equal to 0 is. That one. That's the first the first successes, 0, Then I come here. Trials, how many were they? This guy did how many operations? 12,
12.
Yeah, they have type 12 there. Then I come here. Probability of success P. What the probability of success P here?
0.85.
0.85. Of course, Excel will calculate Q automatically now because P plus Q is equal to 1. So you don't need it here. Excel does it automatically. Then I go to the last one here. The last one. Cumulative. Then I told you cumulative probability distribution. Read it down here. If you want cumulative, here, the one we did here, the less than one is what Excel gives you. Then you type there true. If you don't want cumulative, you type false. So, and it is down here, read. It is a logical function, it's down here, cumulative. You read it. So me, I want the actual the probability, I don't want the cumulative. So I type here false. I'm typing false. Then I come here. I come and do okay. So I've gotten my first value. It is here. It is 0. Can do it 2 decimal places, 3 decimal places. That you see, 0. Then I copy it everywhere. I copy this everywhere. And you can see this is the same as that. Clear? Clear? Hello?
Yes.
So that is getting this from Excel. That's what you can get from there. Then I go with this side. Cumulative. Suppose I want cumulative. I can also, the only thing Excel can only give you this incidentally. This one, not this one. So again, come here. I just pick this one here and I bring it here. Then I come here. I go to binom.dist here again. Binom.dist. Click B all the way. I click D all the way. Then that's binom.dist. Do okay. The same thing. Probably that x equal to 0. I pick x equal to 0. I pick x equal to 0, which is this one here. A successful surgery is here. The number of trials were 12. The probability of success here was 0.85. Then, of course, now I want cumulative. Now I do true. Now I say here true. I need cumulative. That's a logical function in Excel. And that gives me that. For x is equal to 0. Then I do it for all. I do it for all. And you can see these things here are the same. That's the only thing Excel gives. These ones, the same. So what is this binom.dist? Binom.dist is here. Binom.dist is here. Let me just show you where it is. It is all these things here is what Excel uses. Excel uses this one, see. This is what inbuilt in my binom.dist. This one. That's the macro. Of course, you can write a macro in Excel to come up with the binom.dist. Then you get, that is just the macro. It uses these 3 columns to calculate P of X. That's what fx function uses. Fx here. That's what it uses. But again, that methodology is used for large real-life problems, where now spreadsheets are key. You can use spreadsheets to deal with those very, very adequately. So what have I done here? What have I done here? So what I've done here, critically, to go back here, is to go to here. So we are back here. Here. Sorry. Just a second, it's hanging a bit. Good. So this is what I've done. All these things. There are a number of other examples here. This is just basically I was using a table to get this probability is equal to 1, probability is equal to 2, probability, whatever it is. This is the binomial table. Binomial table, which I told you a sample of a binomial table. A sample of a binomial table. And I want to look at this structure because sometimes some of you would love tables in practice. So a table, the first column here is n. N. In our case, n was 12, so this would have been 12. So X values should have come from 0 to 12. Here, N is equal to 6, 0 to 6. N is equal to 3, 0 to 3. N is equal to 2, 0 to 2. Ours was 12. There's no 12 here. I just give you a short table. This is the probability of success. They are here. 0 0.01, 0 0.05, 0 blah, blah, blah. You can see there's no 0 0.85 here. 0 0.85 here. So if I were to show you how to use this table here, I would go and change the N is equal to 6. Then pick a probability of success is equal to 0 0.4. So I want you to do the following. Just write somewhere, pick some rough paper. I want to show you how to use this table. That's what these tables these days are redundant. But just put X is equal to 0. Below that, write 0, 1, 2, 3, 4, up to 6. Please, write somewhere. 0, 1, 2, 3, up to 6. Just like we did in for surgical operations. Then the column, second column, P of X. The X column is this. P of X, now I want you to write there. Pick this one. This one here, 0 0.047, 0 0.185, 0 0.311, 0 0.276, all these, pick this, So this X equal to 0, X equal to 1, 2, 3, 4, 5, 6. Write them somewhere. I want you to go and compare. Just put the two columns, X column 0, 1 to 6, and then of course probability of success we picked here 0 0.4. That's for my use anyway. 0 0.4. You done? You have to show it to you this table, So I go to my Excel, back to Excel, to show you that you get the same thing, Same thing. I go back to Excel. I come here. I'm just going to change this table a bit, for that purpose, Where's my Excel? Where's my Excel? That's my Excel. Now Excel, that one I took 0 point what? 0 point probability of success I took as 0 0.40, 0.40, So I'll change this to 0 0.40. 0 0.40. Then of course N now is not 12. Don't copy this, I want to show you, because just leave the other one, I'll undo this, So that is 6 now. So N is 6. So if N is 6, I go 0, 1, 2, 3, up to 6. That one. N minus X, of course, is 6 minus 6 minus that, So that is 6 minus 0 all the way. And of course, this is N minus X factorial. And of course, this is X factorial. Of course, this is P power X. P power X is okay. Then, of course, you have Q power N minus X. Good. Which is the same, The same, really. It's the same here. Then, of course, you have this. This is what you have, I can tell you. This is what you have. And we'll bring it here. That's what you have. This is what is in your table. This column is what is in your table, with the corresponding values here. X equal to 0, 1, 2, 3, 4, 5. That's what you have. Binomial table. And again, I repeat, nobody really bothers much about binomial tables anymore, because Excel FX can do these things perfectly, because you can never get those values of P if you don't have them. If you don't have them, you can't post them. You have to go to Excel to deal with those issues. And that's one of the key purposes of the spreadsheet. So then, we have done all this. I'm just going to show you what we have done. So a survey indicates that 41% of Kenyan women consider reading as their favorite leisure time activity. You randomly select 4 women. That's the number of times the experiment is performed. And ask them if they're reading, they read for leisure. And you got a response, yes and no. What's the probability that exactly 2 of them said yes? You know, here n is equal to 4. X is equal to n is equal to 4. So you can get either 0, 1, 2, 3, 4. Possible successes, yeses. You can have 0 success, yes, up to 4 yeses. Then you can get at least 2 means X is greater than or equal to 2. Fewer than 3, fewer than 2 is X is less than 3, than 2. And the solution is here. This is the long method, that X equal to 2. Of course, you got the factorials, 4 factorial over 4 minus 2 factorial, blah, 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 blah. You can check this. This is what we did in tabular form. You will get this value here. All of this, that is exactly that to be greater than 2, at least 2. You add 2 to 3 to 4. That is at least that's greater than or equal to 2. That is what you would get. Then of course, then at least 2 women. Again, they are there. These are Kenyan households. Again, we can use a table there. This is the probability distribution table. This is the corresponding histogram. Okay, among others. Then the means are here. NP, variance is NPQ. Standard deviation is the square root of the variance sigma, which is the square root of n, which of course is what we are getting here for that example. And that Rift Valley problem, 50% of the days of the year are cloud, meaning that that's a probability of success, cloudiness. Cloudiness is success, so P is equal to 0.57. So therefore 0 is equal to 0.33. Sorry, 43. Find the mean, the standard deviation for the number of cloudy days. NP times NPQ. All that, they are here, among others. And that is binomial distribution. So you have this in your PowerPoint presentation. And then, of course, I will send you this Excel. I'll send you this Excel incidentally. Then you can review it. I'll let it write Kidogo. I'll also try to convert that into YouTube. I'll send you. Then you can review it, and that will be done. But let's not bother with Poisson today because this is online. And then we can deal with Poisson face-to-face next week. So we stop there.
Prof.
Yes, please.
I had a question.
Yes, please.
When you're showing us how to do the fx function, you said that the cumulative will only be for CPL.
Excel.
So how do you do
that failure of Excel? Excel has weaknesses, Excel can only give you the less than one. Let me just go there. Let's not theorize. Excel does not have, to do that, you need to write, you can write these things in Excel yourself. But again, that one you need to research on your own, how to write those macros, to do what Excel cannot do. Because Excel has these limitations, So Excel can only give you this. Where were we? I know that's where you ask, where you are. Excel can only give you this. This one. This one here. This one. This one here. Clear? That one. That's what Excel can give you, nothing else. But if you want to use Excel to get this one here, to get this, what you do is basically to invert these things. You know what I would do? You know what you do? You go the long way if you don't want to write a macro. What you do is to do the following. I'll show you what you do. Let me change this one first, so that it is clearer for you. What's the probability of success? That is the same thing. Let me just go check. Let me undo what I did here. Let me undo what I did here. Then we go back to what we had before. Where to get the same result. You view what I'm saying here. So this was the greater than one. This is what Excel does not give you. This one here. This one. So what I would do, if I didn't want to write a macro, all I would do, you know how fx function works, eh? It adds from up, eh? So what I would do here was basically to invert these things, eh? I would invert them. I would invert, I would come here. If I want to use fx function, I would have come here and just inverted this, eh? Do not inverted, let's have a minute. So let me just come here, x. Then this is 12. This is the first value of x. I take the highest one here, the highest one, here. Then I just do this, minus 1. Minus 1. There is here. Then I get this. Using cumulative. Using fx. Come here. I do this. This. If I wanted to, but I need to write a macro. I come here. Then I know here the first one here is 12. Because that's where I am. Then I do the number of trials here are 12. Now the first value here is a cell reference. And with the cell reference is 12 here. I'm in the wrong place. I come here. I do B. I do my B because Excel cannot give you this. Excel does not have this option of the at least one. So I do B. B binom dist. That is the one. Come here. The first value is a cell reference, which is 12 here. The number of trials, of course, are 12. The probability of success here is what? The probability of success here is 0.85. 0.85. Then I want cumulative true. And that's the first value of x. First one there. Then I come down here. Do it like that. See the weakness of Excel? See the weakness of Excel here? It does not show you, it does not get, I know I didn't invert this properly. I would have inverted this. You see what you need to do is that this one here, the x equal to 0 should be the 1. But you know what it does? It communicates upwards. It adds 1 to this downwards. So this one Excel cannot give you. This one. Excel can only give you this. This one here. Therefore, to do this, therefore, you must manualize. You go macro way. Of course, you can write a macro if you want. So that's the weakness of Excel. That's why when you reach there, then Excel now becomes redundant. You can't use, now you have to go to the worksheet way. Just use the worksheets, the normal worksheets, the standard worksheet operations, which is what we did here, rather than the fx function. So that's it for binomial. Any question, please, again? Paul, is it okay? You're getting
Yes, it's okay. Thank you.
Good. Any other issue?
Prof, are you able to drop the Excel on the chat, or you send it later?
Huh?
Are you able to drop that Excel on this chat, or you send it later?
Drop it. Anyway, where's that? Let me send it to you now, let me send it to you now.
Yeah. Yes, you can just put it in. Okay.
Let me send it to you now. But I'll send it to Nani. To where is it? I save it,
Peter, I'm listening.
So I sent you this,
Oh,
Yes?
yes.
Nikutumie sasa hivi,
Yes.
Can you send them,
Yes.
Okay, sawa sasa hivi tu. So forget about the register today, Yes, I think they are all here, They just forget about, So you can deal with the register from next week.
Next week, okay.
So this class base bus. So just a minute here. Go to your group C, That's 6,
Yes.
5, 5C. You can just leave. I'm sending. So if I'm sending to him just now, I have his email, So just now, then by in a few minutes, I atakutumia, It's this now. Okay. There's no.
Prof, please take care when you're saving it. Also, just make sure you save it as an Excel instead of a web page. You see that option where you're putting the file name?
I know what I've done. I know what
Yes,
I've done.
hapo
That's
chini,
okay. That's
hapo
okay.
chini
I
weke
know
pia
what's the
ikuwe
problem
Excel.
with you. Sorry. Sorry, kabisa. Yes, I want to say. Let me just save it in your folder. That will be fine. September. Fine. September. And here. Then fine. Consent,
Okay. Me check.
So you send them,
Okay.
Thank you, Prof. Enjoy your weekend.
Asante. Umepata?
Yes.
Nimemtumia, mwambie nini.
Pro,
Eh,
I haven't received it yet.
angalia. Na bado iko njiani lakini iko.
Okay.
I've confirmed it's there.
Okay.
Sasa.